And this example was R2 over R. And what so far we have got is that we have a basis for this, the standard basis. And then we had, just let me go back to that. So, तो उल्टे हैं. Okay, so this was the example. So V was R2 over R. And with respect to the standard inner product, the standard inner product means, so if the vectors are say x and y with the coordinates say x1, x2 and y1, y2, then the inner product is x1, y1 plus x2, y2. And suppose W is the subspace of V spanned by the vector say 1, 1. That means every element is a scalar multiple of this 1, 1. That is alpha, alpha for every alpha in R. And if you take some two other vectors, say 1, 1 and 1, 2, call them say U1 and U2. Then the set B2 consisting of these two is also a basis. This can be easily checked that U1, U2 are linearly independent and they do span whole of B. You can also check that this neither of the two, neither this sorry, this 1, 2. 1, 2 is not there because 1, 1 is there. Is in W. U1 and U2 are not orthogonal. Their inner product is not 0. It's easy to see. As the inner product is 3. And since we were doing Gram-Schmidt orthogonalization as an application to obtain an orthogonal basis from the basis B2 consisting of U1 and U2. So what did we do then was applied the Gram-Schmidt orthogonalization process. And in that process, W1, W2, two vectors to be obtained, which are orthogonal and they span as well as linearly independent. Orthogonal, once you prove, they are linearly independent. So taking W1 as U1 and W2 as U2 minus the inner product U2 W1 divided by norm of W1 square W1. And if you substitute for these vectors, then W2 turns out to be minus half and half. Now it is easy to check that W1 and W2 are orthogonal because their inner product is 0. So this set B3, which consists of W1 and W2, namely 1, 1 and minus 1, 2, is an orthogonal basis for VF. Once you have an orthogonal basis, you can also obtain an orthonormal basis. To get an orthonormal basis, what you have to do is just divide every vector of the basis by their norms, respectively. So you get an orthonormal basis, and we call this as B4. So the orthonormal basis turned out to be minus 1 by root 2, 1 by root 2, and minus 1 by root 2, 1 by root 2. Now let us see from here. Let us see from here the orthogonal complement of W. So recall for an inner product space V over F. So if W is a subspace of an inner product space V over F, an inner product space where F is R or C, the W orthogonal is the set which consists of all V in V such that V comma W 0 for every W in W. So this is orthogonal to everything. So if we want to determine in this setup, then what shall we have? So let us say B, the vector xy belongs to W orthogonal, and take first W. The first vector which is in the basis say 1 1. Now V comma W should be 0 inner product. So this is x comma y inner product with 1 1. This should be 0. That means what? X into 1 plus y into 1, that is x plus y should be 0. Now x plus y is 0 means y is equal to minus x. So what is the orthogonal W therefore is that it consists all vectors, and we also know that its dimension is 1. That we had already seen. Because the dimension of W is 2, dimension of W is 1, and dimension of V is 2, and therefore by the theorem that V is direct sum of W and W orthogonal, dimension of W orthogonal is 1. Which you can otherwise also check that you can take inner product with the other vector and also get the same equation. Y is equal to minus x. So that makes that W orthogonal is basically consisting of vectors x and minus x, where x is a real number. So this is same as x and 1 minus 1 for every x in Rf. So that means this is spanned by say 1 minus 1. Now this is to denote the subspace spanned by this. This is also same as if you want this or this. So a basis for W hat W is over F is simply a set consisting of just 1 minus 1, or you can take minus 1 or this. So this is an orthogonal basis you can check here. And if you want an orthonormal basis here, so you can get this as orthonormal basis. So it's 1 by root 2 minus 1 by root 2. Likewise, you can also have minus 1 by root 2, 1 by root 2. So geometrically, if you want to see, then what is W and what is W orthogonal? So let us see what is happening geometrically. So what is W? So first of all, what is V? R2 over R. So R2 over R, so this is whole your V. You can say this is x-axis, you can also say this is y-axis. All right, now what is W? So W is here, as we had already seen, it is spanned by 1, 1. And therefore this is y is equal to x. So this is actually the line passing through origin. And the point W1. What is W1? 1, 1. So what is it? You can see that this is basically the line that passes through origin and the point 1, 1. So this is the line y is equal to x. So this is W. And this is the point, you can say this is 1. Now what is W orthogonal? W orthogonal consisted that when x plus y is 0 or y is equal to minus x. So this is the line. So you can see this is the line passing through the origin and the point one minus 1 or minus 1, 1 is the same. So you can see that 1 minus 1 is the point somewhere here and minus 1 is somewhere here. So you can check that this is basically the line. So this is the point here corresponding to this. So this point is 1 minus. Likewise, you can see that this point here 1, 1. This is W orthogonal. And this is the line y is equal to minus x. Y is equal to minus x. And this is the line y is equal to x. And obviously you can now see that W is this, W orthogonal is this. And when you take the intersection of these two, the intersection is just origin. So you can observe here क्या हो गया?
Sir, select green pen, right side of that pen.
Green.
Yes, sir.
अब आ जाइए.
Yes, sir. Change the color black.
Okay. तो मैं तो ऐसी पतली रह गई. तो उड़ जा रही है.
Select the pen green one. Sir, select the pen green, right side of that.
Green. अब
black. Color black. Just put.
black. अच्छा यहाँ से black.
Yes, sir.
आ गया भाई. Okay. So observe that. So W and W orthogonal, they intersect only at origin. You can also see that when you sum up So W plus W orthogonal. So every element would be an sum of an element from W and some element from W orthogonal. So this consists of some element of W will be alpha 1 1 plus beta 1 minus 1. And this will be of the form, so alpha plus beta, and this is alpha minus beta. Alpha plus beta, alpha minus beta. So alpha plus beta and alpha minus beta, if they are equal, when are they equal? You see, in that case, alpha cancels and 2 beta is 0. So that will make beta is 0. But if beta is 0, in that case, this is alpha alpha. So that will fall on the line y is equal to x. So that will be there. And likewise, when this is alpha is equal to minus beta, when alpha is, that will fall in on the orthogonal case. So you can put this as gamma, this as delta. And in case both of them are equal, they will force that this is 0, 0, that is the origin. So this is your gamma delta. And this element gamma delta, gamma is in R, delta is also in R for every R, so that is actually pole of V. So you can see that their direct sum is basically pole of V. So V is the direct sum of W plus. You can note that standard basis is always an orthonormal basis. So standard basis means this. Now, one example that I do is for higher dimension, as you can obtain here and can see geometrically. You can also see R3 over R if we do, but then calculations will be. So I do a few calculations and will be leaving for you to verify. So for the sake of clarity. So this is the next example. That is the example 2 or 3, whatever it is. So this time let us say V is R3. V is R3 over R. And let us take 3 vectors. Say V1 is 3, 0, 4. V2 is minus 1, 0, 7. And V3 is 2, 9, 11. Now then you can verify that this is basically a basis. That is for you to see that they are linearly independent, they do span, and so it's a basis. So this is a basis. So say B2, B1 we are reserving for standard basis, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. So V1, V2, V3 is a basis. You can also check that this is not an orthogonal basis. As you can take inner product, for example, V1 and V2. So this is with respect to the standard inner product. The standard inner product here R over R will mean that correspondingly you can x1 y1 plus x2 y2 plus x3 y3. So this is 3 into minus 1 plus 0 into 0 plus 4 into 7. So this you can see is your minus 3 plus 28. So this is 25 and this is not 0. So this is a basis that is for you to verify. This is not an orthogonal basis, so you can see that you just take the inner product of V1 with this. And then this is not an orthogonal basis. All right. Now apply the Gram-Schmidt orthogonalization process. To B2 to get an orthogonal basis. Say B3, W1, W2, W3 for V over F. V is R3, F is R. So what you do is that W1 is simply take as V1. So this is V04. And W2 is V2 minus inner product to V2 with W1 divided by the norm of W1 square W1. Now you can check the inner product of this V2 W1 as 25. Just now we had seen this. This is this V2 W1 is same as V2 V1. V2 V1 inner product is same as V1 V2. So this is same as, so you can now substitute here for V2. So V2 is minus 107 and so minus. Now here the inner product of V2 with W1, as I said, is same as inner product of V2 with V1, which is same as inner product of V1 with V2, which we have already calculated as 25. Then norm of W1 square, norm of this V1 is square. So this is x1 square plus x2 square plus x3 square. So this is 3 square plus 0 square plus 4 square. And then you have here W1. W1 is 304. This is the coefficient of 304. So if you look at it, and this is minus 107 minus. Now numerator is 25 and denominator is 3 square plus 4 square, 9 plus 16, 25. That also is 25. So this cancels and give you simply 1. So this is 304. And this you can see easily is minus 4 and 0. 7 minus 4 is 3. So this is 3. So this is your W2. And W3. So W3 is basically, so V3 minus V3 V1 inner product divided by norm of W1 square. You write V1 or you write W1, it's the same because V1 and W1 are same. But if you write the formula, you should write properly. This here is the coefficient of W1. So this is coefficient of W1 minus. So V3 W2 product divided by norm of W2 square W2. This I leave for you to do the calculations, and I am sure that you will get this vector as unsubstituted as 0, 9, 0. So that makes this, you can also verify that you have got orthogonal vectors mutually. W1 inner product with W2 is 0, W1 with W3 is 0, W2 with W3 is also 0. So an orthogonal basis, therefore, orthogonal basis, let us say, B2 that we have got is, so it's W1, W2 and W3. W1 is 304, W2 is basically minus 403, and W3 is 0, 9, 3. All right. So from here, orthonormal basis also one can obtain. Gives orthonormal basis as B3. So what you do is W1 by norm of W1. So call them, say, U1, U2, U3. What is U1? Is W1 by norm of W1, and norm of W1. So this is the square root of 25, because we had seen norm of W the square is 25. So this is 1 by 5. So it's 1 by 5, T04. So this is same as 3 by 5, 0, 4 by 5. U2. U2 is then W2 by norm of W2. W2 is minus 403, and norm of this U2 is W2. W2 is minus 403, so that square, norm square is minus 4 square plus 0 square plus 3 square, so that again is 25, so norm is again 1 by 5 minus 4, 0, 3. This is minus 4 by 5, 0 and 3 by 5. Finally, it's a U3 now is you can see that this is 0, 9, 0. So norm of this is 1 by 9 naturally, and the vector is 0, 9, 0. This is 0, 1, 0. So this is an orthonormal basis for R3 over R. So now to exhibit once more the same thing, that I take some subspace W of V and obtain its orthogonal complement, and show that their their direct sum is same as V. So next, let us take that W is the subspace which is spanned by, say, V1. So let us take now W to be this subspace of V spanned by V1, like U. So V1 is 3, 0, subspace of V. V is our R3 over R. So what does it mean that elements are alpha times 3, 0 for every alpha in R, or is same as 3 alpha 0, 4 alpha in R. So find out now, find out W orthogonal or orthogonal, and also an orthogonal orthonormal basis. and an orthonormal basis for V over F. F is R and V is R. So once again, suppose so for this, let us take that some vector, say U is in W orthogonal here. Then this inner product U with W is 0. This is true for every W in W. So suppose the coordinates, so if the coordinates of U, say U1, U3, then the inner product, this U comma W is 0 means what? Inner product is U1, U2, U3 with every vector in W. W, so basis vector, if I take 3, 0, 4, is 0. So that makes that this is your 3U1. So 3U1. And then 0, so U2 times 0. So this is 0. And then you have 2, 3 into 4, so 4U3. So this is 0. 0 here means 0, 0, 0, 0 of V. So that makes that we have got 3U1 plus 4U3 as 0. So you can take that U1 and U2 to be arbitrary, and U3 can be taken in terms of, so this is say U3 in terms of minus 3 by 4 U1. So U therefore is U1, U2, U3. So U1, U2 and U3 can be minus 3 by 4 U1. Where U1, U2 in R are arbitrary. Once they are arbitrary, you can easily see that the dimension of W orthogonal is 2. Which we otherwise also know that this over F is 2. This you can see that this is 3 minus 1 is also 2, dimension of V minus this, but otherwise also this is clear from here that this is 2 because U1 and U2 take arbitrary values. Now you can also see that giving a particular value to U1 and U2, two linearly independent vectors, say for example, so this also you can also observe that so U can be seen as a linear combination of two vectors. So for example, you take this as the linear span of, say, U1 you can take say 1 and U2 you can take 0. In that case, this is one vector, another vector. So take U1 to be 0 and U2 to be 1, and therefore this is 6. Now you can easily see that these two vectors are linearly independent. They do span whole of so W orthogonal is contained in the linear span of 1, 0 minus 3 by 4 and 0, 1, 0. This. Now each of them is in W orthogonal. that gives me W orthogonal is the linear span of the set 1 0 minus 3 4 and 0 1 this. So a basis for this we have got orthogonal complement of W consisting of two vectors, say namely 1 0 minus 3 3 another is 0 1 0. So you can obtain some other basis also by giving different values to U1 and U2. This could have been done by taking say some other vector also, for example V1 as W1 W2 3 as orthogonal vectors, and then also you could have done. So this is the linear span. Now this is also the same as if you want, this is the same as linear span of, you want to check this for you to verify, take, and this is minus 4 0 3 and 0 9 0. So this is for you to verify, and this you could have done by taking another set starting with. So this is for you to verify. So you can verify that this is also. So this is also a basis for this. So remember this W. Now recall W. Recall W. W was spanned by V1. V1 was 304, and this was alpha 304. Alpha in R. Now what is it? Now this is a line. So this is a line. So this is the line in R3 passing through origin and this point 3 0 4. You can see the equation of the line, equation of such a line for equation of the line. So you can see this is, so the line passing through 2 points. So this is x minus 0, it passes through origin, and this is 3 minus 0, this is y minus 0, and this is 0 minus 0, and this is z minus 0 by 4 minus 0. So say this is alpha. So this gives you that x is 3 alpha, y is, these are the direction ratios 3 0 4 if you want to say, and then z is 4 alpha. So y actually is alpha. So and W orthogonal. What is W orthogonal? That here is the span. So this is one typical point 304 if you want to see when you put alpha as 1. And W orthogonal is basically the linear span. If you check, this is the linear span of, that's what we have proved, of the set 1 0 minus 3 by 4 and 0 1 0. So any U in W orthogonal, therefore, is a linear combination here. So U is x10 minus 3 by 4 plus y01 0, and that is simply x y and minus 3 by 4 x. That's what we know also already. So this is x, and this is for every x in R. So this represents a plane. Now this represents this W orthogonal, so represents a plane. So what is this plane? Passing through origin, x equal to 0, y is equal to 0, and the point back to 2 points, what they are? 1, 0 minus 3 by 4 and 0, 1, 0. Recall the equation of the line, equation of the plane which passes through the points. So how you can write, suppose the plane is say, so the plane say plane is Lx plus My plus Mz is equal to 0 if it passes through the origin. So let for this be the plane that passing through origin. This is the equation of a plane which passes through origin. Lx, L, M, N are the direction ratios. Now it passes through these points, say 1, 0 minus 3 by 4 and 0, 1, 0. So this will give you some equations. So it passes through 1, 0 minus 3 by 4 and 0, 1, 0 gives us that so this is there. So you can substitute for x, say for example 1, for y 0, and for z say minus 3 by 4. So this point, if it falls on P, tells me that this is L minus 3 by 4 and 0. So passing through this, so this makes that so this implies that L minus 3 by 4 n is 0, and because of this m is equal to 0. And so if you substitute here, what you can get is that so x plus you divide by L, so x plus n x plus n by L z, this is and y arbitrary, this is the plane, or this is x plus 4 by 3 z is 0, y arbitrary. So this is the equation of the plane, x plus 4 by 3 z 0 and y is arbitrary. So x plus 4 by 3 z equal to 0 is the plane, and any point on this plane will be. So W orthogonal is the plane given by the equation x plus 4 by 3 z equal to 0. Naturally, y is arbitrary, or you can also write that z is equal to 3 by 4x. And here y is arbitrary. Okay. So any point would be naturally x, y minus 3 by 4 x. So any point on the plane, any point on the plane is of the form x, y and minus 3 by 4 x. It is easy to verify that this plane is orthogonal to the line. It is easy to see that this plane is orthogonal to the line, or the line is orthogonal to this plane. What was the line L? The line was x by 3, y by 0, and z by 4. So these are the direction ratios here, 3, 0, 4 for this. So DRs are the line and the normal are same, 3, 0. So what you can draw now the picture also if you want to see that you have a plane which passes through these 2 points, 1, 0, minus 3, 4, 0, 1, 0. So if you want to see the picture, x, this is y, z. All right. So this, if you want to see the plane which passes through 1, 0, minus 3 by 4 and 0, 1, 0. So the plane, let us take the plane. So 1, 0, minus, so this is here 1, and then you have 0, and then you have minus 3 by 4. So that will be here, this point somewhere. And like that, you have another point 0, 1, 0. So this is x, z is 0, and your x is 0. So this is on the y axis. So this will be the point 0, 1, 0, say for it. So this is one point. And other point was that you had x is 1. So this is 1. And then y is 0. And z is minus 3 by 4. Z is minus 3 by 4. So somewhat this is positive z. So this is negative z. So this will be 1 and then 0 and then minus 3 by 4. So the plane would be somewhat like this. And the line that passes through the origin and this point, the point is 304. 304 will be 0, that will pass through somewhere here. So this will be orthogonal to this. The line will be like this. And naturally, this is the direction ratios of the line and the normal to the plane are same, and therefore these two are orthogonal. So we had seen now enough of the examples. So I leave for you to do some more examples. One important theorem, let me come back to what we have been talking about, was that. So what was the theorem was at the same time one more thing also we can do is what is known as the orthogonal projection. So recall what we have proved is for a finite dimensional vector space. So it is an inner product space so that V is the direct sum of subspace and its orthogonal complement. As I said that the theorem holds even for infinite dimensional inner product spaces. This theorem is so important that there are so many proofs available for that. One we have already done, and if time permits, we shall be doing another also. At the same time, since we have been doing this direct sum, so in the same sequence, we can also see what is called orthogonal projections, etc. But before that, let me see what is called the approximation. And approximation of vector, and then what is called the best approximation. So it's best approximation. What is best and what is the whose approximation? Okay, so let us take P or F, where F is R or C. Be an inner product space over F. And let us take V be a vector in V. Set W be a subspace of and W be a subspace. Now, so we define that a best approximation to V by vectors in W is a vector W naught in W such that the norm of V minus W naught is less than norm of V minus W for every W in W. So what we can see here is so norm is also called length. So norm of V minus W means so the length between V and W naught is always less or equal to the length between V and every vector in W. Such a W naught, if it exists, is called the best approximation of V. So one theorem that I state, but we shall prove it next day, is the following. So this is the theorem. Let us take this is the theorem which we intend to prove. So in this context, that V be an inner product space, W is a subspace, V is in V. So number 1, the vector W naught in W is a best approximation of V or 2V in V by vectors in W if and only if the inner product of V minus W naught with W is 0 for every W in W. That means what? That is if and only if V minus W naught belongs to W orthogonal. Other things also can be proved, that this 2V can prove that if W naught in W is a best approximation to V, then it is unique. Third thing is, if W is a finite dimensional subspace with an orthonormal basis, for W F, then these W's can tell the exact form of W naught. In that case, W naught will be, so it's the vectors, let us say M. So K is equal to 1 to M, BWK, norm of WK square WK. Naturally, this is the unique and best approximation. And this is unique already we have proved from part 2. Best approximation V by vectors. So we shall stop it here for today and start. Okay, so thank you very much for your kind attention. We wind up here.
Thank you, sir.